Welcome to week 5 of the course. Up until now, you have seen 4 important techniques in the field of parameterized complexity, including branching, kernelization, iterative compression, and randomized methods. In the next coming 2 weeks, we will be doing another important tool techniques in parameterized complexity, which is called tree width. Okay, so before we before we come to the definition of this new tool or new technique, we will go back and start looking at or design an algorithm for another problem. So the problem which we are going to deal is called MIS, or maximum independent set. Okay, MIS. So input is going to be G, and we need to output an independent set of maximum size, right? So we are looking for we would like to output an maximum independent set of size as large as possible. Okay, so it's basically a complement of minimum vertex cover problem, where our objective is to find minimum or smallest size subset of vertices such that every edge has an endpoint, and in the outside or in the complement of minimum vertex cover, it's a set of vertices that do not have any edge contained inside it. So it's a complement of minimum vertex cover problem. So inspired by our minimum vertex cover algorithm or the parameterized vertex cover algorithm, let's try to construct an algorithm for minimum independent, for max independent set, parameterized by size of the graph. Okay, or either word, parameterized by n, the number of vertices. In literature, these are also called exact exponential time algorithms, okay, or moderately exponential time algorithms. Okay. So what is our generic algorithm will be? So the generic algorithm for this problem will be the way as follows. Okay. So here is a graph G on n vertices, right? So the algorithm basically does is the following: finds a vertex V with some property, and recursively builds a MIS. What does that mean? So I take at this vertex V and we say, or we branch now, we say either V is part of maximum independent set or V is not part of the maximum independent set. If V is a part of the maximum independent set, then what can we say? Well, so maximum independent set, so if I have to write a small recurrence, it will be going to be max independent set of G is equal to max of V is in the maximum independent set of G. So if I'm the kind of maximum independent set I'm looking for, either that contains V or it doesn't. If it contains V, then the maximum independent set cannot contain any of its neighbor. So the problem reduces to finding 1 plus maximum independent set of graph minus neighborhood of V, or let's write it better, Vg minus closed neighborhood of V. All right, or it does not contain V in the maximum independent set, then the maximum independent set of G is same as the maximum independent set of G minus V. So this becomes maximum independent set of G minus V. Okay, so this is it, right? Now if I look at what does it reduces, so notice that in one branch there are two branches, and when V is in the maximum independent set, the size of this is going to be at least n minus this, and in this side it is n minus 1. So the recurrence running time is governed by T of n is T of n minus 1 because of this, and T of n minus neighborhood of V. Now if we want to get as good running time, we want to select V. So this is exactly what we do here, right? What we do? We select V such that G size of such that the size of is minimized, and that precisely happened by selecting a vertex of highest degree, right? And so by coming up with some simple reduction rules and everything, you can actually you can show that we can always select V such that degree of V is at least 3, because if the graph has degree at most 2, you can solve the problem in poly time. So this recurrence will lead to T of n being T of n minus 1 and T of n minus 4, and it should lead to some good number like 1 point. Let's see how much is 1 comma 4. What is 1 comma 4? Let's see. So 1 comma 4 solves to, yeah. So 1 comma 4 solves to 1.3803. So this will be like 1.3803 to the power n algorithm. Excellent. Now I want to understand that what happens that rather than find a vertex V with small property, recursively build a MIS, we do as follows. Okay, and suppose we are lucky or whatever, we will come to that. I want to find a vertex V such that the size of a connected component in G minus V is minimized. Okay. So what I want to find a vertex V such that if you delete V, there could be several components. Okay. Size of these components are as small as possible. Okay. Now, why am I asking us to do this? Because then the running time of these algorithms, if you notice, is going to be, so what will you do? So again, we will say, so suppose V has two components, okay, right? So G minus V at least gets two components, and say both has size say n over 2, n over 2. Okay, it's a great, like, now notice that the running time of this algorithm is going to be, what will you do? So in one side, when V is in the solution, what will you do? Well, then the running time of this algorithm is going to be G minus, you will delete neighborhood of V. Then it's possible that what are you going to get is like you will delete V. You might also delete some of its neighbors, right? Right? And here. Right? You will get smaller components, or suppose in other branch, when V is not in the solution, you are still guaranteed to have two component of size at most n by 2. And in this case, you might have many components, but each component has size at most n by 2, because we only had two components of size at most n by 2, and now if you delete more vertices from these components, you can only get smaller components, but not more than n over 2 size. So the running time of this algorithm, if you notice, is going to be, okay, T of n is going to be, so running time for this is nothing but I can write it down summation T of ni. Okay. Suppose it leads to several components of say n1, n2, nl, and so I going from 1 to l. This is one side. This is when V belongs to the solution, and look at this, when V does not belong to the solution, then you have summation I equal to 1 to t, say t of n1 tilde plus, okay, because they only have two components, so let's just write them down explicitly. T of say n1 tilde, and say this is n2 tilde, n2 tilde. Okay, so this is what the recurrence is. And now, if we can ensure that in every iteration, every recursion, we are able to find a vertex V such that it has two components, okay, and no component has size more than n over 2. Okay, and for now, let's just believe that, like, even here, no component has size, no component has size. We also assume that no component, or all component has size less than n over 2. Okay. Now, what happens in this case? So now if you are able to do this and able to do this recurrence, then let's look at the picture wise. What is happening? I have my graph N, and suppose I create two subproblem here of size n over 2 each, okay, and then I create another sub because every iteration I am able to, for every component of the graph, I am able to find a vertex such that if I delete it, both has a smaller component of size at most half of what it is. Then you will get n over 4, n over 4, n over 4, so on and so forth. So the running time of this algorithm is T of n, right? And suppose you are able to do okay, so this is going to be, right, 4 times T of n over 2 plus, say, some time to find f of n is time to find the vertex V of desired kind. Okay, and you can show that this is order some this is like some polynomial. Okay, this is like some fixed polynomial. It is n to the power big O of order 1, and yeah. So what I'm trying to tell you that it's a very nice that this algorithm, which is exponential in general, but suppose you are guaranteed that in each time you are getting a connected components which are at most half of my original instance, then the running time of this every time you want to branch, you are able to find a vertex such that you are able to decompose, you are able to delete one vertex and get smaller connected components, then the running time of this whole algorithm is actually polynomial and it's not an exponential. Now, I will construct such an example soon for you, but just to keep in mind what property am I using, and one property that I try to use in this algorithm is that this vertex had a very interesting property that this vertex was able to separate my graph or partition my graph into two parts. No part is very big, okay? Like what is happening, because now the running time of the algorithm is you are summing the running time of these algorithms, like, and sum of two smaller instances in the terms of exponential will be much smaller compared to say n minus 1 size instance, okay? So if you'd like to exploit these kind of properties, now, hey, I did this and it worked out very well, but maybe you might think that I'm talking about some sort of imaginary graph classes. So where are such graph classes where I could find such kind of object or such kind of recurrence, okay? So let's just try to do maximum independent set on paths, and just to make things interesting, let's add weights, a positive weights on the vertex set of G, okay? And what we want is to find max weight independent set of G. And what is the weight of a set? So weight of a set S is summation V in F weight of V. So you would like to find an independent set such that, and if I sum the weights of the vertices in this independent set, that is maximized, okay? So now what is given to me? What is given to me is some path V1, V2, Vn over 2 and Vn, and there are some weights, okay? And just to be let's write them Wn over 2, Wn, okay? So now let's look at the middle vertex. This is the middle vertex. What is the property? The property is, what is the property? Delete Vn by 2 has a property that you get connected components of size at most n by 2. Now, if I branch on this, what will be my branching algorithm? We'll say, like, here it is, V n by 2 is in the solution, or V n by 2 is not in the solution, okay? So now what happens in this case? If V n2 is in solution, then you are looking to find a maximum weight independent set without, like, so suppose these are its neighbors on the path, okay? Then you are trying to find a maximum weight independent set here, like up to here and up to here in this case, right? In these two components. So in this case, what is the size of this component? The size of this component is at most, these two components had size, the size of the components are, in this case, is at most n by 2 minus maybe 1. But in the other case, I'm saying that, look, I'm not looking to contain V n by 2 as my max weight independent set. Then what is my component size? Is at most again some n by 2, okay? So basically, and notice that recursively, what is the property? So now if I give you some small piece of subpath and I want to find a vertex such that both parts are equal, that's again very simple. You look at the subpath and find the middle vertex of that subpath, and that will satisfy the property that every component has size at most half of whatever we started with. Now, it implies that for this family, the running time is T of n is 4 times T of n over 2, okay, and plus some constant to find the middle vertex. And we can show that this is like at most order n square time algorithm. So yeah, I mean, the algorithm which I talked about is like a single vertex branching. That's great. Okay, but so path was very simple example. Path was very simple family of graphs. What other graphs are there where we should be able to find such kind of algorithm? So let's say, let me write down another family of graph. Let's call it, I call it, let's say, wide path or fat path, whatever you want to call it, doesn't matter. So basically, it's a, so let's look at the grid. Okay, so this is like some k cross n grid, meaning there are k rows, R1, Rk, and there are n columns, some n columns. Okay, so this is why I'm going to call it a k cross n grid. So notice k equal to 1 is nothing but a path. Okay, and now notice that here we may not have a one vertex. Okay, here I can't say, I look here not one, but there are k vertices which has a property that if we delete these k vertices, then every component has size at most half of the original. Great. Okay, so this is a very nice. Here I don't know how to look, because if I just delete one vertex, you will this grid you can't even you can't even disconnect them, right? I mean, okay, but if you look at the middle, suppose this is like somewhere n by 2. Suppose this is n by 2. Now look at this k vertices, k. This k vertices. If I delete this k vertices, then there is a well defined left side and there is a well defined right side, and each side contains half the vertices, right? And each side contains half the vertices of my graph. So now I would ask myself, is that can I exploit these k vertices on this like n by 2th column, and the answer is okay, fine, let's try to do it. So but now there are k vertices. I don't know. So now let's look at the picture. Picture is that here is our grid, and here is our left side. Okay, here is our left side, and here is our right side. Left, right. Now I want to find a maximum independent set, right? So the maximum independent set could have some intersection with Cn by 2 column, right? We don't know what that intersection is. So what is this? So basically it's like a partition x comma y of column n by 2, and what is this? X belongs to solution that we are seeking, y does not belong to the solution. Now notice, what can we say about it? Okay, fine. Here it is, x is there and y is there. Okay. So first of all, if I am looking for a solution that contains x, check whether x is an independent set or not. Okay. If it is not, then this branching of x comma into x comma y is not a valid branching. So assume x is an independent set. Now what can we say? Okay, fine. If you are going to contain x, then two things you cannot contain: neighborhood of x, no way. Like, then you can't contain neighborhood, like open neighborhood of x, right? And you can't, and by definition, y is not allowed. Then basically what happens? So maximum independent set becomes, notice, okay, max over x subset of, say, column n by 2. Okay, that's one thing. X is an independent set, right? And it is side of x, because that you are going to contain. And this is nothing but max if of which graph? G minus closed neighborhood of x union y, right? But notice this graph. Definitely we remove column n by 2 from G and maybe some more vertices, right? So what happens? So we are creating 2 power k sub-problems, right? So when, remember, in path we had 2 power 1, 2 sub-problems, and in each we are going to solve problem on 2 connected components, right? On 2 connected components of size actually at most n over 2. It means our recurrence in this time is going to be T of n is 2 power k, right? 2 power k sub-problems. In each there is one more sub-problem. So that is like 2, and the size is like n over 2. This is exactly what we are going to solve it. Now, so basically if you extend this recurrence, you are going to get 2 power k plus 1. Then again you are going to get, right? Again you will get some 2 power k plus 1 times t of n over 4, and so on and so forth. So this is going to come 2k plus 1, but how many times? Log n times, right? Because n by 2, n by 4, n by 8, n by 16, so on and so forth, and in log n terms, this is. So you are, and so this is why this is upper bounded by this, and if you do this, it is going to come to you roughly n to the power 2 power log n is n to the power k plus 1. Okay, this is the roughly this is the running time of this algorithm. Okay, so notice that this is a great strategy, that if a family of graph has a property that for any connected component, okay, for any connected component, what is the property? That for any subgraph, there exists a vertex of some size, whose deletion has a property that every connected component has small number. So this tells us a following family of graphs. So let's define this following family of graph. So to do that, I will take a path backward, and let me define some simple notion. So now let me define some simple notion. Okay. Okay. So let me define. Okay. A sect X is called a balanced separator okay. A sect X is called a balanced separator of G if in G minus X every connected component has size at most Vg, okay, over 2, right. So this is my first definition. Okay. Okay. Now let me define. This is like a separation number of G. This is max over, okay, max over, okay, okay, max over V prime subset of Vg, okay, balance separation number of graph induced on V prime. Now, what is this balance separation number of graph induced on this? This is basically, what is this? Minimum sized balanced separator of G, okay, of graph induced on V prime, okay. So what is a balanced separation? A set of vertices such that, a set of vertices such that if you delete it, every component has size at most the half of the graph. And so basically what happens is the balance separation number of G is minimum size, balance separator number of G is minimum size is a basically, let's say, size of a minimum sized balanced separator, okay. So like, what is the smallest size subset whose deletion has the property that every component has size at most half of the original, is the balance separation number. And what is the separation number of graph? You go over every vertex set of my graph and say, hey, what is the balance separation number of this? Meaning, for any induced subgraph, what is the minimum sized vertices which does this job? And I take maximum over this. So for example, look at this example of very nice example. Here is a, say, here is a click. Okay, click on say n by 2 vertices, and here is another clique on say n by 2 plus 1 vertices. Now, notice that if we delete this vertex, which is one vertex, okay, if we delete this one vertex, then you get that every connected component has size at most n over 2. But now, look at the cliques, look at a clique, right. You can't delete less than n by 2 vertices and have a component of size at most half of what you started with, right. So, if you wanted to get a component of size n by 4 from this clique, you at least need to delete n by 4 vertices. So, if you notice that although the balance separation number of the G itself is 1, okay, balance separation of induced subgraph could be much larger. So, you can show here that the probably the what is the balance separation number of this graph? I claim that it is at least n over 4, and you check this out. Okay. But what is a vertex, what is the separation number of family of paths, right? So, but separation number of family of paths is 1. What is the separation number of family of k cross n grids? It is k, right. So, it seems like that if a family has small separation number, then we can exploit it algorithmically. Okay. So, this is the this is our mantra, that if a family has a small spatial number, then we can exploit it algorithmically. Okay. Here is an exercise. Exercise, or convince yourself. Let H k be subgraphs of k times n grids. Okay. Okay. Then expression number of H k is at most k, right. So, not only look, and then what we have shown? We have shown that maximum independent set, what we have shown is that maximum independent set, in fact weighted MIS, let us call it WMIS, can be solved in time n to the power big O of k on HK, because there was nothing that we used about the grid, because all we used in the algorithm for this is that, hey, find a k-sized balance separator, okay, you branch on possible ways, and then you solve a problem recursively. So, the theorem which we have proved, okay, let us call it Zk is family of graphs, or rather say, what is Zk contains? All those graphs G such that the separation number of G is at most k. So, what have we theorem we proved? Theorem we proved is that weighted maximum independent set on this can be solved in time n to the power big O of k, right. Now, notice that up until now we looked at the family of paths. So, so let us just try to recall. So, the point what we made is that MIS algorithm works very well if, or the basic MIS algorithm works very well if we can branch on a vertex or a subset of vertices such that remaining component after deletion of this set, after remaining component after deletion of this set had size at most half of the original. Okay. So, this is what we saw first. Okay. And secondly, we saw that subgraphs of k cross n grids are one such example. Okay. So, let me end this class with two questions, and we will try to find answer to these two questions in the coming lecture, in the next lecture. So, what is my question? My first question is weighted MIS fixed parameter tractable parameterized by k on this? Okay. That is a question number first. Second, what other natural families of graphs that has small separation number, small SPN? Example, maybe trees. Okay. So, that will form this answer to these two questions will form the main genesis of next lecture, and hopefully from there we will be able to get a definition which will be useful for our purposes. Okay. So, that is all for the first lecture on tree width. We will connect back later